Hi everyone, can you hear me? Okay, so hello everyone, good evening. Now today we are going to see some of the questions from IP fragmentation. Okay, so before that, let me just recall you that what we have studied in IP in the theory lectures. So yeah. So now we are currently at the network layer, and the most popular protocol at the network layer is IP. Okay, so this is the IP header that we have seen in the theory lectures. I think the lectures are, I'm not sure. I think the lectures are not yet uploaded, right? So you might have seen from the previous year folder, or maybe like I will upload just after this class, if those are not uploaded yet. Okay, so this is the IP header, and IP fragmentation lectures. Okay, yes, I will upload them just after the class. So I hope like a little bit knowledge you have, right? So about this. Is this okay if I continue taking the reference that you have seen this basic of this earlier from my lectures? Okay. So this is the IP header, and it is having few fields, which is like version, header length, and these fields, right? And yeah, so if you look at this IP header, then the header length is just a 4 bits. So in the 4 bits, you can represent at max how much? In this 4 bits you can represent at max like 0 to 15, right? So you can represent 15, so which means that but the IP header could be of 60 bytes, so it could range from 20 bytes to 60 bytes, but the IP header length is just having 4 bits. So that is why whatever is a header length, what I need to do, I need to divide that with the 4 such that I can represent that with the header length field, right? That is what already given in the lectures. So suppose that your header length is actual length is 20, then I will be writing just 5. If actual length is 60, then I will be writing 15, like that. Okay. So this is the header length, this is the version and all. So yeah, so these are the different fields, and TTL is one of the field. So if you are forwarding some packet, then before you forward, then you will decrement the TTL. Now, let's suppose this TTL is 1. If this router is forwarding the packet, then it will make the TTL 0. And if this is a destination, then the destination will accept it with TTL 0, but it will not accept it with TTL negative TTL. In fact, like if this TTL is 0, if this is a router, if this has to forward to the destination, then TTL 0, it will discard. Okay. So basically, whenever you are forwarding some packet, at that time you decrement the TTL, which means TTL 14 you receive. Now, when you are forwarding this, then you will decrement the TTL to 13, like that, right? Why we are using TTL? So that some packet do not get into the loops. Okay. So if your destination is receiving with TTL 0, then it is okay. But if the intermediate router is receiving with the TTL 0, then the intermediate router will discard. Okay, because it has to forward the packet, and then TTL will be negative, which is not allowed. So that's why that if the intermediate router is receiving the TTL 0, then it is it has to discard. Now inside this IP header, I will put everything that is coming from the transport layer. So transport layer will add its own header and all, but that is okay, right? So this is a payload. In this payload, TCP or UDP header, whatever, it will be there in the payload. Okay. So the header length could be from 20 to 60 bytes, and the total length of this IP datagram. Datagram means payload plus the header. The total length could be from 20 to these many bytes, which is 2 power 16. Right. So this total length, if you see here, like the total length is 16 bits. So that is why you can represent the 16 bits in this. Till 2 power 16. 2 power 16 minus 1. This could be the total length from 0 to 2 power 16 minus 1. Okay. Now there's a checksum field, and if you're calculating the checksum, then you just need to, if checksum is, let's suppose some bytes, maybe let's suppose it is of 8 bytes or 16 bytes, whatever, right? So in this case it is of 16 bytes. Then what you will do, you will, as I told you, that you will first take the summation of all. You will carry this wraparound. I mean, you just add this wraparound 1, and then whatever it is coming, you just take the 1's complement, you put in this checksum, right? So that's how we calculate the checksum. Now, now after it, we have solved few of the questions where like IP header is given to you, and now from this header you need to deduct some information. Maybe what is the version and what is the header length and all, right? So if header length is 2, it means the actual header length is actually 8. Okay, so these are the examples, like if this is the total field is this and whatever. So these are the examples that we did. So this is the one of the IP header that we have, and then they have asked maybe the TTL field. Okay, they can ask anything, maybe the total length, because the IP header is given to you. So based on that, you need to deduce some information. Okay. Now, based on this payload, okay, so suppose that this is the header of 20 bytes, and then there will be a payload. Based on this payload, we need to decide, can we forward this packet to the network or not? Which means there is something called maximum transmission unit, okay, that is called MTU. If that MTU is lesser, then you have to fragment. So let's just see what it means. So this is the MTU. MTU basically has like MTU is defined at the data link layer, which means that it is the payload of the data link layer. Okay, so let me just copy this diagram. What I mean to say, see, so suppose that I say MTU is 1500, then what does this mean? It means that data link layer, okay, data link layer can carry 1500 of data. Data link layer can carry 1500, okay, in its frame, in its frame. If this MTU is 1500, which means that suppose that IP header is 20 bytes, then it means that you can, from the network layer perspective, you can carry only 1480 bytes of data. Right? From the data link layer perspective, you can carry 1500 bytes of data, but from the network layer perspective, since there is one IP header, you can carry only 1480 bytes of data. From the TCP layer perspective, let's suppose this is also 20 bytes. Okay, from the TCP layer perspective, you can carry only 1460 bytes of data, and that is called maximum segment size. So based on the MTU, we decide MSS. Okay, so we will talk about the MSS later in the TCP lectures, but here I'm just telling that based on the MTU, MSS is decided. Okay, what is MSS? Maximum segment size that TCP can carry. What is MTU? Maximum transmission unit that you can transmit over the data link layer. So if the MTU is 1500, if these are the 2020 bytes, then the MSS will be just 1460. Okay, this much data that you can carry. And who is providing you this data? Application layer. Application layer will provide you this data. So this is the hierarchy, right? Okay. So MSS is determined using the MTU, right? That's what we have written here also. Now let's suppose that you have a IP header of 20 bytes, and there is a data of 5000 bytes. But this MTU, like I mean, you have some channel, and on that the MTU, on that network, the MTU is just 1500 bytes, which means that Ethernet header can carry only 1500 bytes. Okay, you are sending some data. This router wants to send some data to this network, but here you are using the Ethernet protocol, and Ethernet, let's suppose the Ethernet have 1500 maximum transmission unit. Then what you will do? You will divide this packet, right? So since it can carry the 1500, so let me just tell you what it is happening, and that's where we have the fragmentation. See, you have, this is the IP header, and you have the data of 5000, right? So suppose this is the IP header that you have of 20 bytes IP, and this is the data of 5000. Okay. Now, if you talk about MTU, then it is saying, let's suppose it is saying that you can carry only 1500 bytes of data, which means including this IP header. Okay. So MTU is basically the data at the data link layer. So this is Ethernet. Let's suppose you're taking the Ethernet protocol, and now in this case there will be 1500 bytes of data that you can carry, which means including this IP. So basically this MTU and everything, this MTU is basically the data. Okay, data you can carry at the data link layer, which means that you need to divide this 5000. Okay, whatever this is, let's suppose this is 5000. So 5000 and this is 20. So total is 5020. So what you need to do, you need to first keep this IP header separate and just divide this 5000 only. Okay, this data part, just divide this 5000 into how much part? Such that see, there will be IP header also, such that each is carrying just 1480 only. 1480. Why? Because this is 5000 that you need to see what they will give you. They will give you the total size of this. This is 520 size, 5020 size. Then first you need to take this IP header separate. Okay, then it is just 5000 bytes. And then if the MTU is given to you, then also you take the IP header separate. So basically always subtract the IP header from the total length, this length, and also the MTU. Okay, so again, see, this is, let's suppose the total length of IP datagram is given to you, which is 5020. Okay, and MTU also given to you, which is 1500 bytes. Then what does this mean? It means that first we need to subtract IP header size, and IP header size is also given, which can be from 20 to 60, but yeah, generally it is 20 only if it is not, even if it is not given. Okay, IP header size is 20 to 60, but let's suppose it is given to be 20. Suppose this data is given to you. This is the question. Now what you need to do, first you need to subtract from this total length, you need to subtract the IP header, which is 20, which means the data. Okay, so here you need to subtract this 20 from the total, which is 5000, and you need to also subtract this 20 from the MTU. Okay, so which means this will be just 1480. So basically this is the actual data that you have at the network layer, and you need to divide this into 1480. Okay, so subtract this 20 from this also and this also. The total length is given, subtract that also. Why that is the case? Because whatever fragments you have, okay, let's suppose you have multiple fragments. This is the Ethernet. Then each fragment you will be having IP, right? IP header. In each fragment you will be having IP header. This is Ethernet. In this fragment also you will be having IP header. So effectively you can carry only 1480 of data. Effectively you can carry only 1480 of data. So that is why subtract this 20 from this total length also, and then from this MTU also. Okay, so you just do this calculation. Like one of the packet will be having 1480, another I think 1480, another I think 1480, and then what is remaining here, you can just do this. Remaining, whatever is remaining will be here, right? So basically it will be divided into 4 parts, and then the remaining will be here. So what you need to do, you need to subtract 20 from both of them, and then you need to divide. So what the actual frame will be containing? It will be basically containing Ethernet frame, and then here it can carry 1500 bytes of data, from which 20 bytes are from IP header, and then remaining 1480 will be this one, first fragment, right? So that's how you need to calculate it. Okay, let me go over the slides. So see here, this is 1480. Yeah. So I mean, whatever is the MTU, based on that you need to divide. So suppose you are sending some packet, and then of this network the MTU is 1500, then you need to divide. Okay, maybe the data is larger, so you need to divide it, and then what you need to do, let's suppose even the MTU even is smaller in this network, then you again need to divide these packets, right? So you may need to divide any number of times, depends on the MTU, right? So see here, this MSS, okay, MSS is determined using the MTU. Based on the MTU, you determine the MSS size. Great. Now let's go to the IP datagram fragmentation. So the maximum amount of the data that the data link layer frame can carry is called MTU. When a datagram is fragmented, each fragment has its own header. Okay, so basically we will be having its own IP header. Each fragment will be having its own IP header. Why that is the case? Because each fragment travel independently. So basically it has to have its own IP header that tell you what is the source IP, what is the destination IP, like that, right? So each fragment travel independently. That is why it has to have its own IP header. Okay, now just think about it. Do each fragment have to have its own TCP header also? Do each fragment have to have its own TCP header also? No, right? Why? Because the thing is that these fragments are basically routing in between the routers, right? I mean, at the end these will reach to the destination, and at the router we do not even have the transport layer, right? We only work with the network layer. So basically at router, if it is router, then it is having one network layer, and maybe like depending on the interface that it is connected to. Suppose it is connected to 2 interface, then it will be having some data link layer header and then physical layer, right? something like this. So basically it does not have transport layer. So at the router, you do not have the transport layer. So that's why you do not need, like you just need the source IP and destination IP. You do not need the port number and all, right? So that's why like you do not need the TCP header for each fragment. You just need IP header for each fragment. Okay. Now, just tell me one thing. Let's suppose this is your complete data, okay, complete IP datagram, which means that this is the IP header and this is the payload of 5,000 bytes, suppose initially. Okay. Now tell me, if that is the case, then where is your TCP or UDP header? Just after this IP header, right? I mean, it must be here only. TCP header, let's suppose. Now, if you're dividing these 5,000 bytes into number of bytes, into number of fragments, then, okay, let's just forget about this TCP header for now. Okay, let's just forget about this TCP header. Let's suppose you're dividing this, then you are saying that, okay, first 1480 will come here, first 1480 will come here, okay, and then this is your IP, and then you will apply your Ethernet header, right? This is how you will do. First 1480 will be here, next 1480 will be here, something like this, right? Next 1480 will be here. This is your IP header, and then there will be an Ethernet header, right? Next 1480 will be here, next 1480 will be here, like that. 1480. Next whatever is remaining will be here. So basically, you will be dividing in number of packets. Now, first 1480, next 1480, like that you will be dividing basically. Now tell me, where is the TCP header among all the fragments? This is the first one, this is the second one, this is the third one, this is the fourth one. Where is the TCP header? Only in the first one, right? Because TCP just after this IP, right? It is in the payload. Okay. So if the first 1480 is still here, right? First 1480 is still here, then TCP is only in the first fragment. Right? TCP header, TCP or UDP header is only in first fragment. Right? Is this okay to everyone? Let me know. Only TCP header or TCP or IP header has to be in the first fragment only, because this works just as a data, and all other fragments does not have it. Do we need TCP or UDP header in between of routers if you are transferring some packet? No, right? You do not need TCP or UDP header for the intermediate routing. You just need the IP header. So this kind of scheme works fine, right? Okay, great. Now let's just move here. A datagram can be fragmented by the source, or it can also be fragmented by the intermediate routers. Okay. So let's take this example. Suppose I'm fragmenting this into 3 parts. Now, whatever is the identification number, it will be same in all the fragments. If this is 100, it will be 100 in all the fragments. If this is 200, it will be 200 in all the fragments. So that at the time of reassembly will happen at the destination, and only at the destination, not in the between, right? Because there is no point in reassembling at the between. Maybe I need to again further divide it, right? So why to reassemble in the between? So reassembly will happen only at the destination, and the destination will be reassembling only with respect to the same IP. If the same ID, if the ID is 100, then only it will reassemble all of them. If ID is 200, it will reassemble all of them, right? Like this. Now there is one more field which is more fragment, which is saying more fragment. If it is 1, then it means yes, there are more fragments that are following. There are more fragments. If it is 0, then I will say there is no more fragment. So basically only the last fragment have this MF bit as 0. Okay, MF flag is 0. DF flag says that do not fragment. If it is 1, then I will not fragment, and empty. If the empty is smaller, then I will just drop the packet, and I will send the ICMP message back to the source. Can anyone guess it, like why source wants to do not fragment or something like this? Why source do not want to have any fragmentation? I mean, why the source is keeping this DFH1? Any guesses? Maybe this source wants to know MTU of the whole network, right? I mean, if it will send some data, and based on the MTU, it will drop and it will send the ICMP message, and it will also put the MTU value here in the ICMP message. So basically, suppose if source wants to know the MTU of the network, then it can do DFH1. so that it knows the MTU of the network, and then it instead of fragmenting at the intermediate routers, it will send the fragmented packet only. Okay. So I mean, just to have again and again fragment. Okay, just give me 1 second, right? Hello. So for 15 to 20 minutes, voice might not be 100% perfect because I'm using my laptop microphone. But after it, like it will be good because that wireless microphone that I have, it just got discharged. So I kept it on charging. Okay. Anyway, so am I audible now? Okay. So suppose you are sending one packet that has been fragmented into 3 packets. Now 3 fragments. Now this bit is 1 because MF1 means there are more fragments, and then at the last it is 0. Now suppose only 2 of them are reaching, which means this is reaching the last one and the first one, but the middle is missing. Then can the receiver get to know that there were 3 packets? Receiver should be, or the destination should be knowing with the knowing that there are more fragments, right? It cannot assemble the fragments which are out of order. It should be assembling all the fragments, otherwise it should not assemble anything. So in this scheme currently, can you tell me, is there any way to for the destination to recognize that there are more packets following? So yeah, currently it's it's not, but yeah, there is a field that is called offset. Using this field, the host, the destination can get to know, yes, there are more packets basically. Okay. So what is this offset? Let's just quickly see that if you're transferring some packet, then the offset basically tells that how many bytes you are following. So suppose that you are transferring this packet 1480, 1480, 420, then this is first packet, this is second one, this is third one, this is fourth one. Since the first packet do not follow any bytes, that's why it is 0. Okay. Second packet follow 1480 bytes. That's why it is 1480. Why I'm dividing by 8, I will just come to this. And then this is 1480 into 2 because this is following how many bytes? 1480 and 1480. This is 1480 into 3, right? Now MF bit will be 111 and 0. ID will be same, right? Now why I'm dividing by 8? Because any in worst case, what may happen? Any fragment can follow can follow 2 power 16 bytes, right? Almost 2 power 16 bytes. But this offset is just 13 bits. Okay. So basically, I have talked about this in the theory lecture. That's why I'm just summarizing it quickly. See here, the offset is just 13 bits. That's why I need to divide by 8. Just like I have divided by 4 in case of header length. Okay. So we divide by 8 so that the scaling works. Yeah. So these are the offsets that we have. Now at the reassembly, what we will be doing, we will be searching for the initially offset 0. We will be searching for the packet that is having the offset 0. Once we get it, we will say, okay, this is the first packet because this is not following anything. This is the first packet, and then we will increment it offset plus the number of data bytes it has divided by 8, right? And then we will search for that offset, which means first we will search for offset 0. Then we will search for offset which is search for a packet which is having offset 1480 divided by 8. Then we will search for the packet that is having offset 1480 into 2 divided by 8. And then we will keep on searching. At what point we will be stopping? We will be stopping when the MF is 0, right? If the MF is 0, we will stop. Repeat it till MF is 0. Right? This is the code which is called reassembly code that we have at the destination side. Okay. So see here that in worst case, there could be just 1 byte and it could follow 2 power 16, almost 2 power 16 bytes. So that is why there will be some scaling, right? Because the allowed offset is from 0 to 2 power 13. So that's why we do scaling. Okay, these were some questions that we did. Suppose that MF this more fragment value is 0, then what does this mean? It means it is last fragment, or there are no fragmentation also. It could also mean there is no fragmentation, right? If this is 1, then is this a first fragment or last fragment or middle fragment? Do we know if the packet was fragmented? If this is 1, then yes, we know the packet is fragmented. It is first, middle, or the last. It cannot be last. It can be first or middle, right? It cannot be last. Could be first or middle. So we can solve these kind of questions. We have already solved in the lecture. So these are the answers. Anyway, we have solved in the previous lecture. Now let's do some of the problems from the gate perspective. I mean, gate PYQs and some standard questions also. So for example, I take this question. Then here it is saying that M2 is 576 bytes, right? And then this is a data part which is 1484 and 20 byte of header. The IP packet has this bytes of header, 20 bytes of header, and the data part. Okay, IP data. This is the IP data. Since the IP data is given to you, then you do not need to subtract. If the total length is given to you, then you need to subtract. So this 1480 you will divide into how much? 556, 556, 556. But since this is 556, which is not divisible by 8, that is why what you need to do, you need to basically take very close to this 556, which is divisible by 8. So 552, basically, right? Why we need to divide by 8? Because of the offset. Okay. So these are the fields. Yeah. Now let's solve some questions that I have. So see here, I've taken this slide from Stanford course. So what they're saying, I think they're saying the almost same thing. The fragmentation when necessary, if M2 is lesser, then you need to fragment. I'm audible, right? And source host tries to avoid the fragmentation. When the fragment is lost, the whole packet has to be retransmitted. So basically, this is very important. If only just one fragment is lost, then the whole packet has to be retransmitted. So that's why the source avoid the fragmentation. Okay. So what the source do? The source does not do not want to do the fragmentation in the intermediate router. It will do the fragmentation at its own end. So that if only one fragment is lost, then you do not need to retransmit the whole packet. Okay. So yeah, this is very, very important. It's not like that if one fragment is lost, then you will just retransmit one of the fragment. No, you have to retransmit the whole packet. Refragmentation is possible. I mean, you are fragmenting something, then you are fragmenting to this, you are passing through this network, one packet, and then let's suppose this get into 2 packets, and then maybe the MTU is even smaller, right? Then you may have to divide this into further 4 packets maybe. Fragmentation is done at the source and at the router. Source means like if whatever is coming from the network layer. So let me just tell you, see this diagram. This is the fragmentation at source, right? So whatever is coming from the transport layer, the network layer will say that, okay, based on the MTU, maybe it knows the MTU, then it will say that, okay, I do not want to transfer the whole data at once. I will transfer in the chunks. So it's a call of the network layer at the source, right? I mean, if it is not the MTU, if this network layer knows the MTU, then it can just divide into chunks at its own side. Otherwise, it does not know, then it can send the whole data. So that's also called fragmentation. Yeah, so basically it's just a terminology. I mean, a host avoid the this source avoid the fragmentation, which means the fragmentation in between the routers, okay, on the network. So source can do the fragmentation at its own, okay, tries to avoid the fragmentation. I mean, source cannot obviously send the whole data whatever it is receiving from the transport layer. Okay, it has to divide that into number of packets. So avoids the fragmentation means fragmentation in between routers. Okay. Yeah, and at the reassembly, when destination is going to reassemble, then it has to delay the assembly until all the fragments are arrived. It cannot reassemble some. Let's suppose there are total 5 fragments. It cannot reassemble some 2 or 3 fragments like that, right? Do not recover from the lost fragments. Okay, so maybe it means that if there are lost fragments, then you cannot recover only the lost fragments. You have to transmit the whole packet. Maybe that's what they want to say. Yeah. So let's suppose that this is the network that we have, and you're passing something, and then there the MTU is exactly as 1400, let's suppose, but later the MTU is smaller. Okay, then you have to just fragment it into number of packets, and then this MTU and this MTU may be same. Then you do not need to fragment. Okay. Yeah, so it depends on the protocol. If you're using Ethernet, generally the MTU is 1500 bytes. If you're using a PPP, which is one of the protocol data link there, which we do not need to note. These are not in our syllabus, but yeah, these are the protocols as the data link layer. So the MTU here is 576 bytes. Okay, so now let's solve this question. What they are saying that IP has, so they are saying this, that IPv4 has provision for the fragmenting and the reassembling the packets. Right? Consider the network in the figure below, where the MTU of the link layer of 3 links, 3 IP hops is listed. So MTU is this much, and MTU is this much, and then MTU is this much. These MTUs include the header of the packet. Yeah, so MTU, you know what does this mean? So basically, this has the header of the IP packet. You can consider the IP packet to have no options, which means the IP header length is 20. Right, header length is 20 with a fixed header length size of 20 bytes. Okay, suppose you send a packet with a payload, and then they are saying fill the table below. So basically they are saying at this link AV, the total length that is traveling, I mean, you are sending one packet which is having 1420 of the total length. Okay, so maybe it is given here also. Yeah, suppose you send a packet with a payload of 1400 bytes on this network, which means the total length is 1420. Fill the table below listing all of the fragments that are transmitted along each link. So basically you are transmitting some packet, and let me just go to the next page. So you are transmitting some packet, and then they are saying that 1400 bytes you are transmitting from A. Okay, from A you are transmitting 1400 bytes, and then plus 20. Total is 1420 at the IP. But you need to divide only 1400, right? Without the header. And the fields are given below. The link field, this link field is not in the IP header, but yes, like other fields are in the IP header. This total and the IP, identification and these things. What they're saying that at each link, okay, the link at AV, your this packet is traveling. At BC, there might be some fragmentation, because this is 700 and then this is only 1400, so there might be some fragmentation. At BC, how many number of the packets that you have? At maybe CD, how many number of the packets you have? That's what they're asking, right? I mean, you need to fill with each link. So let's solve this question. This is just an easy question only. So see here. Okay, so what they're saying is this, that you are transmitting a packet of 1400 bytes that has to divided into how many, what is the size of this? 700, but it should be 700 minus 20, which is 680. Is this digital 8? 680? Tell me. Is this digital 8? So, yeah, this is digital 8, right? So that's why you do not need to worry about it. Basically, you will divide this 1400 into 680, and what is remaining here? It will be 0, 4, 60 will be remaining, right? You will be dividing this 1400 into 680, 680 and 60. Is this okay to everyone? Why 680? Why not 700? Sorry, 40 should be remaining, right? 0. Yeah, 40 will be remaining. So basically, why 680? Why not 700? 700 is empty, but you need to subtract 20 from there, right? You need to subtract 20. 700 is empty, but you need to subtract 20. Okay. No, that's okay. 700 is not divisible by 8, but you need to subtract 20 first to transmit the data. So there will be 3 packets on this BC link. Now see here, the MTU here is even greater. Do you need to fragment at CD? So whatever you are transmitting at BC, okay, the same thing you will be transmitting at CD also. So the same 3 packets you will be transmitting at CD also. You do not need to fragment again. Now, what will the total length of the first packet? It will be 700, right? 700. 680 plus 20. What is the identification number? It will be same. Identification number will be same. Do not fragment of the first packet. Obviously, it will be 0. Everywhere it will be 0. Do not fragment. If this is 0, it will be 0. More fragments are following. Yes. What is the fragment offset? Initially, it is 0. What is the time to live? See, it is forwarding some packet. So the time to live will be some even lesser, right? It will be 254. 254 here for these 3 packets, right? One lesser. And what is the next packet? What is the total length? Total length will be 700 only for this packet, right? The total length is 700 only. Identification is same. DF is same. More fragments, yes. What is the fragment offset here? How many bytes it is following? It is following 680 bytes, but divided by 8. So what is this number? It should be 85. Okay. Yeah, it is 85. So now you will see that fragment offset for the second packet will be 85. For the first packet is 0 because it is not following anything, but it is following 680 by 8. It is following 682 into 680 by 8. So it means for the next packet, the fragment offset will be 170, right? And do we have more fragments? No. What is the DF? This, and what is the total length? Total length will be 40 plus 20, which is just 60. And this is TTL. What about the CD? CD will be having almost same, but the TTL will be just lesser, 253, 253. Right? TTL will be just lesser. And everything else will be same. CD will also be having the same packets. Because there is no more fragmentation apart from this BC. Okay. So CD will also be having the same packets. I hope that is fine. No, last fragment offset you do not need to divide. Like this could be anything because that offset you are not taking anywhere. So that's why this could be anything. This do not need to divide by 8. Okay, this could be anything because you are not going to write this anywhere in the fragment offset calculation. Yes, that is right. Okay. Now let's move to more questions. So now let's just solve some of the gate PYQs. I think I have many gate PYQs from this IP fragmentation. So this one, yeah, I think I have all of the gate PYQs now. Then we will be seeing some ARP or some questions from the ARP. So let's solve this question. These questions are actually easy, to be very, very honest. If you want, you can try as an homework. These are just few questions. I mean, there is no trick or something like these questions are very easy, but let's just try here. Consider the following statement about the functionality of the IP-based router. A router do not modify IP packet during forwarding. Tell me. At least it modifies the TTL, right? At least it modifies the TTL. So that's why this is false. It is not necessary for a router to implement any routing protocol. This means you do not need DVR or anything. Yes, that is true because it can always use flooding. It can forward in all the direction if it doesn't know the way to forward, right? So it do not need to use any routing protocol. Yes, that is true because it can use flooding. What is the third statement? A router should reassemble IP fragments. No, it should not reassemble, right? If the MTU, no, it is false, right? So this is false. So only, I think second one is true. D is true. Yeah. Yeah, reassembly is only a destination. Now let's solve this question. In IPv4 datagram, the more fragment is 0, header length is this, total value is this, the fragment offset is this, the position of the datagram and the sequence number. Do you want to try this question? This question has been asked in GATE 2013. I think this question is easy one only. Okay, you can try it as an homework. The solution is on the next page. Can you try it as an homework? These are just easy questions. So that's why like there is no trick. If you want, you can try as an homework. Okay, this question is easy one. Now, is this okay if I just quickly leave this for the homework? Let me know. Okay. So now let's do this next question. Yeah. Okay. So consider the IP packet that is having 500 bytes that includes 20 bytes. Okay, this question, let's just try this question. I mean, in this class itself. Okay, you just take 1 minute and just solve this question. Okay. So is there any change in audio quality now compared to the quality that you were receiving earlier? Little bit of change in audio quality. Do you feel? Okay. Have you tried this question now? So this is saying that consider an IP packet of length 4,500 bytes that includes, okay, it is including the IP header, ANS, and I think it should be and 40 bytes of TP and TCP header. So this 4,500 bytes includes the IP header and the TCP header. Okay, so the IP header and the TCP header and everything is just a payload. So the total length is 4,500, which means this one is 4,500. Sorry, 4,480. Right, this one is 4,480 because the IP header is of 20 bytes. The packet is forwarded to an IPv4 router that supports a maximum MTU of 1600 bytes, right? So this you have to divide into 1600 or how much? You have to divide into 580, right? 580. Assume that the length of IP header in all the ongoing all the outgoing fragments of this packet is 20 bytes only. Assume that the fragmentation offset value stored in the first fragment is 0. The fragmentation is stored in the third fragment. So basically, this is 4480 that you have to divide into 580, right? That's all. So let's just quickly do it. 580. Is this digital 8? This is not exactly digital 8, so that's why there should be 576. Maybe this is 576, right? And then how many 576 will be there? Like what they are asking actually? They are just asking the fragment offset value in the third fragment. So this is first fragment, second fragment, third fragment. So here they are asking the offset value. So how much offset value is there? Offset here is 0. Here it will be 576 divided by 8. Here it will be 576 divided by, into 2 divided by 8. It is, I think, 72 is correct. Yeah, it is 144. So okay, these are the fragment offset values for this packet. That's all, right? Suppose they ask you to have the fragment offset value for the last packet, then what it will be? Let's suppose they give you, okay, I mean, you need to calculate, let's suppose for 10th packet or something. How many packets, how many fragments will be there? Number of fragments, can anyone tell me? You need to check number of fragments. So in that case, you need to divide this 4480 by 576, right? And then the seal of this, then let's suppose this is 8. So there are 8 fragments, and then let's suppose they ask you the offset at the last fragment. Then what you need to do? You will be multiplying 576 by how much? 7, right? 576 into 7 by 8. 576 into 7 by 8, and that's how you can calculate. So basically it will be 72 into 7, which is, which is 504, right? Yeah. So this is the offset at the last. So they can also ask these kind of question, not just third, they can ask for the last or something. Actually, there is no innovation like I have found particularly in neither in GATE PYQs nor in somewhere else. Yeah, there are few good questions that I found, but I will put that in the test series directly, okay, in the mock test. So the good questions were looking like that in 2-3 universities. I found that they have not given the MTU even, okay. So this MTU was not given to us. They just asked that what should be the MTU such that like this. I mean, like that, some calculation based question only. Okay, that I have put in the test series. I mean, I will be putting in the mocks. So in the mock 4, probably I will put some that kind of question. Okay, so 144 is the correct answer. Now let's see this question. What they are saying, IP router with the MTU of 1500 bytes has been received, and the IP packet size of this. Okay, so I think these questions are easy. Probably you can do it a normal, right? Now see, in this question they try to confuse you with the TCP header, which is a 40 bytes. Does this matter to us? No, right? I just like what does matter? This IP payload. This is the only thing that matters to us, not the TCP header size. Okay. Or if they ask you that I mean, which fragment is containing the TCP header, then only the first one, right? Only this one. Only this fragment contains okay. Yeah. Again, this question maybe you can do it now only. So let's spend 1 or 2 minutes. Just try to do it. Okay. So what they're saying, host A sends a UDP packet of this much bytes of user datagram to host B over the Ethernet line. Ethernet may carry data up to this much. So UDP datagram containing these much user bytes. So basically there is a UDP header, and then you are having 8880 bytes here. So then you will be having, there will be a TCP header, IP header. Then you will be having how much payload depend on the UDP header size. It is 8. So basically they have given the UDP header so that you can calculate the total size, which is 8888. Okay, this is the IP payload to which I need to work with. And then there is no option field. So IP header is 20 bytes. So what you need to do, you need to divide this 8888 into 1480, right? So just do this and get the answer. So see here, this is 8888, this is 1480. There will be 7 number of fragments, and then you can find out the fragment offset for the last fragment. Okay, that's easy question. You can do it. TCP per UDP header will be added to the data unit. Okay. I hope you understood this question. They've asked, I think, the total number of IP fragments that will be transmitted and what consists of the offset for the last fragment also. Great. If there are 7 fragments, then the offset for the last fragment, you need to multiply by the 6 only. Let's see this question. This question has been asking GATE 2004. What they are saying, a TCP message containing of 2100 bytes is passed to the IP for the delivery across 2 networks. The first network can carry payload of this, and the second network can carry this much. And yeah, they've asked this is an easy question. I think you can do it, right? Total IP overhead in the second network. Okay, IP overhead means like total number of bytes that you are using for the IP headers, and including all the fragments. So maybe you can do this, right? Or should I do this? I think this question seems little tricky. Let's just try this. Or maybe you can spend 1 minute and then I will try doing it. Okay, just spend 1 minute in doing this. TCP message containing of these many bytes is passed to IP for the delivery across two networks. The first network carry 1200 bytes per frame and the second network carry this maximum payload 400 bytes per frame, excluding the network overhead. Okay, so assume, so basically 1200 bytes means it should be 1180, right? 1180 that you have, and you are passing these many bytes is passed to the IP for the delivery. Okay, so this is the actual data. So 20 like this 2100 that you have to divide into and like 1180. Okay, and then this 1180 should be divided into again into 380. Just try it for a minute and then I will solve it. Okay, I think this 1200 they have given and the 400 they have given without the overhead, right? Excluding the network overhead. So I think this should be 1200 only because it doesn't contain the IP header. Network overhead means it doesn't contain the IP header. No, bottleneck and all you do not need to take. There are two networks. First, it will be divided. This is the MTU of 1200, and then and not MTU. Basically, MTU could be larger, but this is the I mean MTU. You can say that it is 1220. I mean this can handle IP without the IP header. It can handle 1200. Okay, and similarly, it can handle 400 without the IP header. So this is 2100 that you are sending. So you can do it easily. 2100, then 1200 in 1200 each you need to divide. First check whether it is divided by 8. Yes, it is divided by 8, right? Since it is divided by 8, you do not need to worry about it. I mean, worry about the scaling and all. So this is 1200. The remaining will be, if you subtract this, then it will be 9. Then it means it should be 900. Is 900 divisible by 8? No, right? Sorry, 900 divided by 8. So it is not divisible by 8. So that is why I will not have 900. So instead I will be having the nearest one. No, basically 1200 minus 20 will not be there because they are saying excluding the network overhead. Network means that they are saying the IP without the IP you are having this 1200 without the IP. Okay, without the IP header. This is not the MTU. Maximum payload that it can carry this much per frame without the excluding the network overhead. Okay, so since it cannot be 900 because 900 divided by 8 is not integer. So what is the nearest one? Maybe let me just try dividing it. It will be 1 and then it is 1, then 1, it is 2, right? So I think if you remove 4, which means it should be 896, right? So 896 is divided by 8. So you can take it 896 and then what is the remaining one? This is 2100. This is this much. So 1200 and 896 is 6, 9, and then 20. The only 4 is remaining, right? So this is 4. So this is the this is excluding the IP header basically, obviously. right? Now let's not add the IP header. I will add the IP header at the end. I mean, here you need to add the IP header to transmit it, but this is the actual payload without the IP header. Now, what is the next MTU? Why 896 we are taking? Because the number 900 is not divided by 8. I need to have something which is divisible by 8. This should be divisible by 8. This should also be divisible by 8. Since it is divisible by 8, so that's why I do not need to worry about it. No, that's not the... Okay, you are saying that's the last fragment. Yeah, that's the good point. Yeah, that is correct also. So that's the good point. Yes, that's the last fragment. So you do not need to worry about it. Yes, I agree. So I think 900 will work here, because if you are keeping 900, then you do not need to keep this entry anywhere else. So that's why 900 will work here itself. Yeah, that is very good point. So now what we need to do, we need to again divide this into 400 bytes. So yeah, 400 without the IP header. So basically this is also without the IP header. So you can divide into 3 parts, 400, 400, 400, right? 400, 400, 400. And then you can divide this into, this 3 parts, I think, 400, 400, and 100. So how many fragments I have at the end? 6 fragments. What they're asking is that, what is the total IP overhead? So total IP overhead will be 6 into 20, right? 120 bytes, 6 into 20, because I have 6 fragments at the end. Since I have 6 fragments, this is after one network, this is after a second network. So that's why 120 should be answered. Okay. Okay, 1200 doesn't contain the IP header, right? So it is without the IP header. Great. So now let's just go to the next question. Maybe you can try this question. This question has been asked very recently in 2021. You just try this question as a homework, okay? So that you have some practice. Now let's just do next set of questions, which are related to basically ARP. So let me just recall what is the ARP, and then we will be doing those questions. So suppose that you this allies wants to send some packet to maybe Bob, that is in another network. Okay, so if it is sending some packet, then it only knows the IP address of Bob, but it doesn't know the MAC address of the Bob. Obviously, like, I mean, it is in another network. It do not also need to know. So what it will do, it will transmit this packet, and then it will say that my IP address is N1 and my MAC address is L1. So, and this Bob MAC address and IP address is L8 and N8. Okay, something like this. Now it will be just putting the MAC address of what? Of the next hop only. Which means, I mean, if it is transmitting to R1, then it will say that, okay, this MAC address is L2. So have you understood this? The IP address is of LIs, source IP address, and destination IP address is also of the Bob. But the source MAC address is of the LIs, and the destination MAC address is of Bob, is of R1. Why? Because this is the next router or the next place that I want to send some data. And then these source and IP will keep on changing. I mean, this MAC address, source and IP MAC address will keep on changing, but you never change this network or the IP address of the source and IP. Source and destination MAC address keep on changing, but the source and destination IP address will never change. Okay, if you're sending from here to here, like I will tell in one of the class, maybe tomorrow or day after tomorrow, that how all of the layers are working together. But for now, just understand that these MAC addresses are keep on changing everywhere. Okay, this is MAC address, this is keep on changing, and the IP addresses will remain same. So that's how we transmit the packet. So suppose, like for example, that this is the host that wants to send to this IP address. Now what it will do? It will send its packet, let's suppose it wants to send to this particular host. So it doesn't know the MAC address. Then it will say that, see, I know the IP address, but I do not know the MAC address. Then what it will do? It will say that, okay, please tell me the MAC address also. So it will broadcast some packet that is called ARP broadcast. So it will say that who has this IP address, right? And then one of them will reply that, okay, it's me and my MAC address is this. So basically, ARP is used to get the MAC address of some device, maybe host or maybe router. So like there are different cases that I will talk about it. So basically this is the host, and if it wants to send to this IP, then it will say, okay, who is the host that belongs to this IP. Then this will reply that, okay, I'm the one. So basically ARP query message is the broadcast. Basically it will be just screaming like this, that who is having this IP, who is having this IP. It doesn't know like who is having this IP. But the reply is the unicast only, because it can reply to this one only, right? So request message is broadcast. It will just broadcast to everyone, and the reply will be just unicast. This is just unicast, means it will just reply to the system A only. ARP reply is unicast. ARP request is broadcast. Okay. And that's how the ARP header look like. I mean, if you are sending a ARP packet, then this is how it will look like, but it is not important to us. Okay, this header and all is not important. Yeah. So what you need to do, ARP is basically encapsulated in data link layer frame. So here you will be having, I mean, some preamble, and then destination MAC address, source MAC address, and then as a data in the data link layer, as a data you will be having ARP packet. Okay. So I mean, these details are actually not much important, but yeah, I'm just telling you that you encapsulate this ARP packet in the data link layer, which means as a data you will be having this packet. And whatever the protocol you are using and everything, based on that, you will be setting up your data link layer header. Okay, I mean, preamble, destination address, MAC address, these are just part of maybe Ethernet header only. So there will be Ethernet header. Okay, so there will be Ethernet header, and then there will be a ARP packet. This is the data of the data link layer. In this is the ARP. It could be the ARP packet also. ARP packet means it might be having, I mean, it must be having its own header also, ARP header. Okay. If it is IP packet, then it will be having IP header, something like this. So in this data, you will be having the ARP packet. Now let's take different cases. Suppose there is a case when the sender is a host and wants to know the MAC address of another host in the same network. Okay. So if this is the same network, then host has a packet to send to another host on the same network, then the target IP address will be the destination IP address in the IP datagram. So basically here, if you are having the host in the same network, then you will be broadcasting again, then the destination, okay, the target IP address here. So basically in this ARP, there is something called target hardware address, sender hardware address. One second. Yeah, these are the MAC addresses. Yeah, this one, target IP address. So there will be a field. See here in this ARP packet, like since you do not have any IP packet here, so in this case, like this target IP address, so this ARP packet will look something like this. It will be having the target IP address, which means that it will check like what is the host that is having this IP address, and then in that host I'm interested in, right? So basically you do not have any source IP or destination IP currently in this ARP packet, right? In this ARP packet, you do not have source IP or destination IP, because source IP and destination IP are the fields of IP header. But do we have the IP header here? We do not have the IP header, right? We have the ARP header here. So if you recall, then in the IP header, I was having the source IP, destination IP. These were the fields in the IP header. But since you do not have the IP header here, you have the ARP header. So ARP header has only the MAC addresses, because you do never need to send the ARP packet out of the network. Okay, within the network we only send the ARP packets. So it do not have source IP or destination IP. It has the source MAC address and destination MAC address. That's okay. But it also has the target protocol address, maybe target IP address, which means it will say that, see, this is my IP address. Okay, so so these are the 4 fields that I have in the ARP. These are the 4 fields that I have, which are important. So I will say what is my MAC address, right? My MAC address, sender protocol address, which means my IP address. This is target hardware address. So that's what I need to know, right? So that's what we need to know. And this is the last one is target protocol address, the IP address of the target, right? I mean, I'm interested to convert this IP address to the MAC address, something like this. So basically, you can say destination IP address. Okay. Yeah. So now you might be wondering that why do I have to send my IP address? Can anyone guess? Maybe let me ask this question just after 5 or 10 minutes. Okay. Let me first go over the slides. Then you may guess this question, answer of this question. So the case one is that when the host is in my network only, then I will broadcast this packet. I do not know that what is the MAC address. So I will broadcast this packet. I will say whoever is having that much IP, please reply me. So it will reply, right? Now there is a case two where the sender is a host and wants to send the packet to another host on another network. Okay, this is a little interesting. So now, yeah, this case is quite interesting. All of the cases are almost same, but still, if we want to distinguish, then we can distinguish. So this is the case two, when sender is a host and wants to send to the packet to the host to the another network. So see here, this is in the another network. So suppose that this is one host A, okay, A that is connected to some network, and then this is the router of this network, and then there is another network in which there is a host which is B, and then maybe this A wants to send to this B. A wants to send some packet to B. Now what this A will do, every host or every router have its own routing table. Similarly, every switch, there are switches that I will talk about. Every switch has its own switch table or the forwarding table. Okay. So anyway, I will talk about the devices in one of the lecture. So here the sender, what the sender will do, sender has its own IP, its own MAC, and the B's IP. This is what sender has, and what it wants to know. Right? Okay. Now, first tell me, do sender want to know B's MAC address? Is this correct or wrong? Do sender really wants to know B's MAC address? I don't think so, right? Why sender is very worried about the B's MAC address? So sender doesn't need B's MAC address. It knows its IP address. Then it will check that, okay, what is the next based on the routing table of this host, it will check that, okay, what is the hope that I should be forwarding it to, right? It can check based on this IP address and the network mask that is given to you. So if you open your laptop IP configuration, maybe there is a subnet mask that you have, right? Subnet mask. In Windows, I think you can open in the settings or something. So basically there is subnet mask and there is IP address of every host. So using the subnet mask, IP address and another IP address, can you identify whether the given host, this B, is in my network or not? Obviously you can identify, right? Whether this B is in my network or not. Since B is not in your network, then what you will do? You will forward this packet to the default gateway. Okay, this R. Then it do not need the B's MAC address. It will need the R MAC address. It will just need the R MAC address. You getting my point? So basically, it do not need the B's MAC address. That's the point. Because B's MAC address is none of its business. It will just need the MAC address of the next hop. Because MAC addresses are keep on changing, right? So if you remember in the first slide, we talked the MAC addresses are something that keep on changing to the every hop. So this is L to L1. Then again, if you look at it, then it will be L5, L4, something like this, right? Then it is L7, L8. So these are keep on changing. So that's why you do not need the MAC address of the B. You just need the MAC address of this router. So what it will do, it will just the target IP address is the IP address of the router. That's what it will put in the target IP address, and then the host wants to know the host wants to send the packet to another host in the another network. It must first be delivered to the router. So it will just broadcast its query, and then it will say that okay, this router will reply with and the target IP address with the IP address of this router. Right? So in the target IP address, it will not put the IP address of the B also. So here, this B's IP address is not used in ARP. Right? So ARP packet, this is the ARP packet. In ARP packet, sender and receive this sender IP and sender MAC address are okay, but this target hardware address will be just blank. This target IP address will be router IP address, not B's IP address. Okay, is this okay to everyone? Let me know quickly. Now, where I am using this B's IP address? Can anyone tell me quickly? Am I using this B's IP address in whole process? I think we are using somewhere. Can anyone tell me where? See, using this B's IP address only, I will get to know there will be a routing table of A. Then, using this B's IP address only, I will get to know that what is the next hop, right? Next hop. Right? Next hop is this R, let's suppose. Okay. So using the B's IP address only, I get to know, okay, I need to forward to R. So basically it is used in the routing table in this like to decide that what is the next hop. Once I know the next hop, if it is B, then I will be using the B's IP address. So basically here I will be using the target this IP address is the next hop IP address. Okay, in the ARP packet. Let me know quickly if things are fine or it is a bit confusing. See, in the ARP packet, mainly I have these 4 fields, right? Mainly I have these 4 fields. So suppose you want to send something. Now this is sender things are clear, right? Sender things are very easy. It's my own IP address, own MAC address. Now target IP address will be just target MAC address will be just blank. Now what is the target protocol address or target IP address? It will depend what is the next hop IP address basically. Basically, if you are sending, if you want to send to this R, if you are sending to B, first you need to send to R, right? And then this R will send to B because it is in another network. So basically, the next hop you have to send to R. So that's why if that is in another network, that is why this target IP address will be the IP address of a router in this case. If that is in the same network, let's suppose in the same network, then the target IP address will be, because based on the routing table, you will get to know that, okay, target IP address will be, it's in the same network, it is just B's IP address. So whether it is a B's IP address or the router IP address, it depends if it is in the same network or another network. Okay. So here, you will not write the B's IP address, you will be writing the next hop IP address, which is the router. Now we are not writing B's IP address anywhere. No, you do not need to put the base IP address. Why you need to put the base IP address? You are not sending the data. You are just sending the ARP packet. ARP packet does not have to have the base IP address, right? When you send the data, once you have the router MAC address, at that time, what you will do? See, once you have the ARP will get you the router MAC address. Okay, this ARP will get you this router MAC address. Then what you will do? You will take its MAC address. Let's suppose this router MAC address is, let's suppose, L2. Okay, you want to send some packet from this to this. Now the ARP packet will not be having N8, right? But the data will be having N8. This is the data. Data will be having N1, N8. That is fixed. But ARP packet will not be having this N8. Okay, ARP packet will be having this N3. and then you will be getting this router, this interface, which is N2. ARP packet will be having this N2, and then once you will be getting L2, you will be putting that L2 here in this, okay, in the data. Once the ARP is finished, then in the data packet you will be putting L2 in the Ethernet frame, and N1 N8 in the IP. B MAC address you never need to know. At this LIs, you never need to know B's MAC address. Okay, you only need to know this R1 MAC address. At this point in time, you do not need to know B's MAC address. I hope that is clear to everyone. Because you just need L1, L2. B's MAC address will be needed at R2. R2 will be needing B's MAC address, then it will be writing this L8 here. You do not need L8 anywhere in the between before this R2. L8 is the B's MAC address, and then you do not need this L8 anywhere in the between. Okay, let me know if that is fine to everyone. Maybe I can explain a little more. See, so basically what is happening here, this will be forwarding some packet, and now you will say that, okay, you want to send to this Bob B, right? This is B, and then this is A. If you want to send from A to B, based on first step is that step 1, check, okay, check A's routing table. It will check that, okay, next IP that it has to forward. Yeah, so A wants to send to B, then what A has, okay, so A has its own MAC address, its MAC address, its IP address, and B's IP address. These are the things that A has, right? I hope that is fine. Then first step, it will check, okay, based on the B's IP address, it will check that what is the next hop. Next hop is R1, right? I mean, this to this it wants to send. So once the next hop is determined, then it will send the ARP to the next hop only, because it wants to know its MAC address. Okay, so since it cannot set directly, because I mean, if it is in the same network, then it works based on the MAC address. So it does not know the MAC address of R1. So what it will do, it will send a broadcast message that it will say step 2 is basically broadcast, ARP broadcast, to know MAC of R1. Okay, so it will send the ARP broadcast to know the MAC of R1. Once the MAC of R1 is replied, okay, so R1 will reply. Then as in step 4, what I will do, I will send actual packet containing IP address of A, IP address of B, okay, IP address of A, IP address of B, because that's the destination IP address, but the MAC addresses will keep on changing. MAC address of A and the MAC address of a router only, not the MAC address of B. Here, this is not the MAC address of B. I do not need the MAC address of B. Okay, when you are sending from A to B, you just need the IP address. And these MAC addresses will keep on changing from this hop to this hop, L1, L2. If this is sending, then L4 to L5, L4, L5. This will keep on changing. These MAC addresses keep on changing, but IP addresses never change. In any packet, IP addresses can never change. Is this okay to everyone? So basically, you will just keep on changing the MAC addresses, right? And then at A, you will never need to know the MAC address of, at A, you never need to know the MAC address of B. You just need to know the MAC address of this R1. Okay. Yeah, so that was the next case that we have. See, in this case, what we do, we just need the router MAC address, not the B's MAC address. So I will be broadcasting and I will get to know the router MAC address. Now the third case is where the sender is a router and receive datagram is designed for the host on the another network. So the same story, then it will just get the router MAC address, right? If that is in the another network, then I will get to know the router address, the MAC address of the next hop. So this is same as the second case. If sender is a router and has received a datagram destination for the design for the same network, this is same as the case one, where the both of the sender and receiver are on the same network. Use ARP to find the host physical address. Yes, only the last router will broadcast it to know the B's MAC address. Otherwise, no one need to know the B's MAC address. Okay. Only the last router will say that, okay, I want to send to B. I have the IP address. Can I get the MAC address? So it will broadcast the ARP. Okay. This third and fourth are same as second. This is same as second one. This is same as first one. If both the devices are in the same network or in the another network, there are only two cases effectively. Okay. So see here, suppose the host IP address is this, physical IP address is this, host IP address and the MAC address are given. Another host IP address and MAC address are also given. These two hosts are on the same network. So the ARP request, if these two hosts are in the same network, it will put as in destination IP address in the ARP as in destination IP address. Okay, the source IP and destination. See in the ARP, what are the four fields that I have which are important? Source MAC, destination, like source MAC, source IP, destination MAC and destination IP. As in destination IP, both are in the same network. I will put its own IP. What is that IP? 130, right? So I will put this 130 in this ARP request. Okay, that is not shown in this picture, but I think. Okay, this is preamble. I think that is not shown clearly. Or maybe this is the one, right? This is the one. They have converted that to the hexadecimal. So anyway, that is okay. So basically, the IP address that I will be containing, if both are in the same network, then the IP address of this B only. If both are in a different network, then I need to know the MAC address of what? I need to know the MAC address of a router. So that's why I will be putting the IP address of the router. So whoever, if I want to know the MAC address of router, then I will put in the IP address of the router here. So basically, if it depends on the thing that to which device I want to know the MAC address. If I want to know the router MAC address, then router IP I will put in. If I want to know the host MAC address, then host IP I will put in, right? Okay. Now let's see a few questions. The address registration protocol ARP is used for finding the MAC address, right? Finding the MAC address that corresponding to IP address. So it is easy question. D is the answer. Yeah, D is the correct answer. Now let's do this question. That question has been asked in GATE 2021. S1 is saying destination MAC address. Consider the following two statements. Destination MAC address of an ARP reply is a broadcast address. ARP reply is a broadcast. Is this true? I think this is false. And ARP request is a broadcast. Yes, this is true. So S2 is true. S2 is true and S1 is false. I think C is the answer, right? It is also easy question. Very easy question that they have asked in 2021. Okay. Actually, in GATE, out of 100 marks, what I feel that literally the 50 marks are very much approachable. Which means if your preparation is on decent level only, okay, not too good also, then also you can get the 50 marks. That's what I feel. And because the GATE, all the questions are not tough. They intentionally put some questions which are very straightforward. Now let's solve this question. Or maybe, yeah, let's solve this question. What they are saying, the diagram below shows two subnet connected by the router. Okay, this is one subnet and this is the router. For each host and a router port, the IP address and the MAC address are shown. Initially, the ARP tables of the host and the router are empty. So basically, ARP table means it has a mapping about what is IP, what is the MAC. So every device has its ARP table, so that it do not need to do again and again request, reply, these kind of things, right? So it is having ARP table, it is having ARP table. This is having, yeah. So this is B is having ARP table, R is having ARP table, A is also having the ARP table. So there are two interfaces. So for one interface it says its ARP table, for another interface it says its own ARP table. Now what they are saying, initially the ARP table of the host and router are empty. Suppose A sends a packet to B. So the content of the ARP table after the packet reaches to B. So if A is sending some packet, then what will A get to know? Tell me. See, if A is sending some packet, then it will get to know which mapping. It will get to know that, okay, this is the IP address, and then what is the MAC address. So I think this mapping that will get here in this A. You getting my point? See, if you're sending something to B, first you need to send to this R. So basically, you will be knowing this mapping, that okay, for this IP address, what is the MAC address. So in this table, you will be having this. Let me know if that is fine. Let's just see here. In this table, you have this, right? Okay. Now, what will be here in this interface, in this router entry? Since you are requesting something, see, do you remember I asked you one question? That why we are putting this MAC address, right? Why we are putting this MAC address here? I mean, if you are sending some packet, why we are putting the source? Sorry, why we are putting the source IP address? Because ARP do not need the source IP address. ARP is within the network, so it do not need the IP address basically. Then why we are putting? Because if you are sending something, then it is good to help others also. So it is just to help others, which means to whoever I am sending, okay, to whoever I am sending, basically they will also get to know that what is the mapping between this IP and this MAC. So basically, if I'm sending to this R, then R will replace mapping that they see this is my IP address, this is my MAC address, and R will also get to know age mapping. Why? Because it's there in the ARP packet. So this interface will get to know age mapping, which means, like I will say that this will be having 1.2.3.1 and A. Is this clear to everyone? This entry will be stored in this this routing ARP. Why? Because whenever you are asking something, then you will get to know, this R will get to know the mapping also. And what are these two entries? Now R has to send to B. So basically R will request for the ARP, right? R will request for the ARP. So what are those entries? R will get to know the B's mapping. So see here, R will get to know the B mapping, which means this mapping. This mapping R will get to know. Right? And now, what are this mapping? This mapping, this B will get to know the mapping of this, because whenever I'm sending some ARP packet, I'm also helping other. So we will also get to know this mapping. Okay. So I hope that is clear to everyone. Okay, ARP reply is not broad. You are saying are also not broadcast. Yes, ARP reply is not broadcast, but ARP is within the network. If something is within the network, you can work with the MAC address only. Okay, you do not need the IP address if something is within the network. And there is some concept called network address translation that I will tell you. But yeah, something is within the network, then if that's the IP address, that is okay. But you can work with the MAC address also. Only with the MAC address. Even you do not need the IP addresses. I mean, if you want to send some packet, you do not need the IP addresses. See here, if you are sending within this network, let's forget about the ARP and all. Okay, completely forget about the ARP. This is the normal data, and then does it have anywhere this is sending to R1? Does this have anywhere N2 IP address of R1? Anywhere do you have N2? No, right? So it can send using the MAC addresses only within the network. Okay. So I hope you understood, right? Yeah. Now let's solve this question. What they're saying? No, ARP request is broadcast, ARP reply is unicast. Now this is not the ARP packet. This is just a normal packet. Just forget about the ARP. This is just a normal packet. If you want to send some normal packet, are you having this N2 here in this normal packet? That's what I'm asking. No, right? You're not having N2 here. So basically, you do not need the IP address of the destination if you want to send within the network. Okay, you do not need the N2. Similarly, you do not need, if you want to send from R1 to R2, you do not need anywhere this N5. You do not need. You need the MAC addresses within the network. So if you want to send, if R1 has to reply, then R1 also doesn't need the this IP address of this LIC, which is A. Okay, R1 doesn't need N1 if R1 has to reply. Within one network, it doesn't need actually. I mean, if it has, it's good, but I mean, like it depends on the protocol that we are using basically. If you're sending with the destination IP address, then also it is good. Otherwise, like if you're not having, then also it is good. I mean, it depends on the implementation, I think, right? But we can identify the host within the network using the MAC address within same network. Okay. So now let's see this question. Suppose C sends out the ARP request. So there's a this is C, right? So this one is C. So what they are saying is, suppose that C sends out the ARP request, then a very first time, which means like there is no table or no ARP cache that you have. How many of the 18? So there are 18 hosts, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are total 18 hosts, right? Now what they are saying, how many of the 18 hosts in the network receive the frame containing ARP request? If C is sending out some ARP request, then how many of these 18 receive the ARP request? See, this is one router, and let's assume that this is one subnet. I mean, this is one network, suppose, okay, and this is another network. So these are the two different networks. So if C send out some ARP request, it will broadcast, and that broadcast cannot cross one network. So basically, this broadcast will be within this network. So how many hosts are there in this network? 1, 2, 3, 4, 5, 6, 7, 8, and then this 9, right? Total 9. So basically, C will send its broadcast message to 8 hosts and 1 router, 9 total. ARP broadcasts are restricted to subnet and do not pass through the router. So all 9 other hosts in the left network will receive the ARP broadcast. Okay, so none of this will receive the ARP broadcast basically. Only these will receive the ARP broadcast if C is sending out some ARP packet. Yeah, so to know the destination in the same network, we need IP. Yes, that is correct. But again, I'm saying it depends on the implementation. Like you need IP, but for the ARP, I'm saying if you're sending the ARP, you know that this is an ARP packet. So that's why you know that this is in the same network, because you cannot receive the ARP packet from another network, right? I mean, you can receive the ARP packet within the same network only, because that is broadcast. Okay. So by default, you know that this is the same network. This is the question that we did. Now let's do this question. Consider the network shown in this figure below. Suppose A would like to send IP datagram to D. A would like to send IP datagram to D. Okay. And assume that A's ARP cache does not contain D's MAC address. Okay. Which means that A doesn't know about the D's MAC address. Will A perform the ARP query to find the D's MAC address? Tell me, is this correct? Will A perform the ARP query to find the D's MAC address? Do A ever need to know the D's MAC address? Yes, it will find the router MAC address, right? So let me check. No, answer is no, because they are not in the same lane. A can find out that they are not in the same lane by subnet by checking the D's IP address. So using the D's IP address, it will get to know, okay, these are not in the same network. Then it will find the this router IP address, right? Not the D's, router MAC address, not the D's MAC address, basically. I hope you understood. Now let's do this. Suppose host A would like to send IP datagram to host B, and neither A's ARP cache contains B's MAC address nor B's ARP contains A's MAC address. So A like to send the IP datagram to host B. Okay, so A wants to send to B only in this case. Okay, so now A wants to send to B, and then what they are saying. Further, suppose that switch forwarding table. So for this switch, a forwarding table contains entries for host B and for the router only. Okay. Thus, A will broadcast an ARP request message. So basically, A will broadcast its ARP request message, right, within this network. And then what action will the switch perform once it receives the ARP request message? So A will broadcast the ARP request message. It will come to this switch, and then what will switch will do? It will just pass the broadcast message to B, right? So it doesn't need to do anything. Just a second. Yeah. So actually there was one more question that is left, but yeah. So coming to this question, switch S1 will broadcast the Ethernet frame via both switch interface as is receive the ARP frame's destination address is a broadcast address, right? So basically ARP destination address will be just broadcast address because I want to broadcast it. So it will be just a broadcast address. So S1 will broadcast it, and S1 will update its forwarding routing table entry for the host A. ARP packet is put in the IP datagram or just no, it doesn't put in the IP datagram, only in the Ethernet frame, directly in the Ethernet frame. ARP has nothing to do with the IP. Okay, IP frame, IP datagram. Now let's see this question. Just try these 2-3 questions. These are just common questions. Let's just try them. Okay, just read them out and take your just 1 minute. Okay. So what they're saying, will router also receive the ARP request message from this above? Will router also receive the ARP request message? Tell me. If so, the forward will it forward to the next subnet? So when A is sending to B, right? So yes, I mean A is sending to B, so it will like the packet will get received to the router, but router will not forward it, right? Because there's a broadcast message, so router will not forward it. So A, like this packet, when A is sending to B, the broadcast message will go to the switch, and then this switch will forward to both of its interface. I mean, apart from the incoming one. So it means it will broadcast to both of its interface, this one and this one, apart from the incoming one. And then router will also receive. Yes, but it will not forward. Yes, that's correct. Now, once host B receives the ARP request message, okay, host B receives the ARP, it will send back to ARP, it will send back the ARP response message. But will it send ARP query message to ask A's MAC address? Will B send the ARP query message? No, right? Because ARP request message itself has the A's MAC address. Okay, so no, B won't send the ARP query message asking for the A's MAC address. This address can be obtained from the A's query message. Let's do this last question. What will be the switch? What will the switch do when it receives the ARP response message from the host B? What will switch do? It will just forward it to A, right? Once switch S1 receives the B's response message, it will add an entry. I mean, it will just update its own routing table that for host B in its forwarding table that see if this is the destination address. I mean, it will just update its own forwarding table and then drop the receive frame as the destination host is on the same interface as host B. What they're saying. Okay, ARP response message, B is sending ARP response message. Then why it is dropping? Once switch S1 receives the B's response message, it will add an entry for the host B in its forwarding table. No, switch doesn't have the network layer. I will talk about the devices in maybe 2-3 classes. After 2-3 classes, okay? Then drop the receive frame as the destination host A is on the same network. Why it is dropping the receive frame? Maybe there should be maybe they wanted to ask something else. If B is sending some unicast message, B wants to send some message to A, then this will not drop. Obviously, like it should reach to A. once it receives the ARP response message from the host B, it will just forward that to A. I think there was some this is the answer of some other question probably. Okay, but yeah, it will send to A. Definitely, it should send to A. Okay. Maybe this is something else. So I hope you understood. Now, in the previous year questions, like I have checked the previous year questions, there are only just 2-3 easy questions. No, why switch is going to discard? When will switch do it once it receives the ARP response message from B? What will switch do? If that is ARP response message from B, then it will forward it to A, right? Switch MAC address and destination MAC address is different. Yeah, that is correct, but it will forward that to to A. It will not, I mean, discard in the sense it will not just drop the packet. It will forward, right? So at least it has to forward the packet. It will not accept the packet as its own packet, but it will forward. Okay. So this is about the ARP and IP fragmentation. So in the next lecture, we will talk about some more protocol, which is BOOTP and DSCP and all, and then we will move to some other topic. Okay. So I think the computer networks is going smooth, which means like I'm taking one topic, I'm solving some of the PYQs and some of the standard questions. Okay. With this, like you should be able to solve all the PYQs or any other question that will come in the gate. Yeah. So thank you everyone. Let's meet tomorrow in morning. Thank you. Take care. Bye-bye. Yeah, we will do those questions. Okay, KS, don't worry. We will do those questions in operating systems also. So I will cover those kind of questions once this computer networks is over. Okay.